Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Physics Paper 2 Higher Tier from 2024. Question number 4 is on the topic of electromagnetism and magnetism. Figure 6 shows two magnets and a wire. There is a current in the wire. A force acts on the wire in figure 6. What is the direction of the force on the wire? So how do you figure this out? We use Fleming's left-hand rule. Now, how does Fleming's left-hand rule works? Let me show you a diagram showing you how Fleming's left-hand rule works. So in this diagram, when you hold your left hand out and with your thumb and your first two fingers out perpendicular to each other, the thumb represents the force, direction of the force. The first finger represents the direction of the magnetic field, and the second finger or the middle finger shows the direction of the current. Now the trick is to align your fingers along with the direction of the magnetic field and the current by rotating your hand. So for that, you need to look at the diagram. So the current is actually pointing upwards. In the diagram that we have, it was pointing down. So let me bring the diagram up so that you can actually see that. So the current is actually coming down towards us, but here it's actually in the opposite direction. The magnetic field is from the direction of the magnetic field is from north to south. So if the current was coming downwards rather than going up, like is shown in here, and the magnetic field direction is correct, the force would have been up, which is out of the paper, or it will be coming up from the paper. But here, because the direction of the current is reversed, the force is going to be reversed. So that is into the page. The length of the wire in the magnetic field between the magnet is 80 millimeters. Now this has to be in meters. So divide that by 100 equals 0.8 meters. Now remember, when we are using distance or length in calculations, it's always in meters. So even without looking at the rest of the question, I know that the length of the wire should be in meters, hence I've changed it already. The current is I equals 4.6 amps. The force is capital F, which is 0.092 newtons. The length is L, which is 0.8 meters. Calculate the magnetic flux density, which is capital B. Between the magnets, use the equation. Now the equation will be F equals B for magnetic flux density, I for current, and L for length. So let's substitute the values. The force is 0.092 equals the magnetic flux density multiplied by the current, which is 4.6, multiplied by the length, which is, hey, I've made a mistake, I've just realized. Converting millimeters to meters, you need to divide it by 1,000. So that will be 0.08. 0.08. Rearranging the equation, magnetic flux density is 0.092 divided by 4.6 times 0.08, and that gives me 0.25. And the unit for magnetic flux density the easiest is Tesla, but you can also, if you forgot how to work out the unit, remember 0.092, that was the force, so you had Newton. Let me use a better color. So this was the force which is in Newton, divided by 4.6 is the amps. So they have given you the units here. So this is going to be in meters. So we are going to use M. So that's amp and meter. So you can write this as the unit as well, and you'll still get a mark if you've forgotten what the unit for magnetic flux density, which is Tesla. So the answer is 0.25, the unit being Tesla, or you can write Newton per amp meter. Figure 7 shows an electromagnet close to a permanent magnet. Here you have a coil of wire around an iron core with a power supply, and you have a permanent magnet. Now, because the switch is closed and you have an iron core, this is the electromagnet. This is going to create a magnetic field, and this iron core is going to become a magnet. If this becomes a magnet, this electromagnet and the permanent magnet is going to interact. Depending on the direction of the current, this could be the North Pole or the South Pole, and if these two poles are like poles, then it's going to repel. If they are opposite poles, it's going to attract. The electromagnet exerts a force on the permanent magnet. The permanent magnet exerts an equal and opposite force on the electromagnet. Which law is this an example of? Now, if a force is exerted in equal and opposite in direction, that's to do with Newton's third law. Give two changes to the electromagnet that would increase the force exerted on the permanent magnet. So what can you do to the electromagnet that would change the force exerted? So the force depends on the magnetic field. So how would you change the magnetic field of the electromagnet? Any two of this will be fine. Move the electromagnet closer to the permanent magnet, which is an option that most students don't actually think of in the first instance, right? You could add more turn to the coil in the electromagnet, or you could say increase the current in the coil of the electromagnet. .5. Give two changes to the electromagnet that would reverse the direction of the force exerted on the permanent magnet. What can you do to the electromagnet that would change? If you want to reverse the direction, you need to reverse the magnetic field. Now, the way you would reverse the magnetic field is by reversing the direction of the current. So what can you do? Reverse the current in the coil. Let me bring that. Reverse the current in the coil of the electromagnet. Or you can turn the electromagnet around to reverse the poles. Or the third option, which is not generally thought of by most students, is to wrap the coil around the iron core in the opposite direction. If you wrap the iron coil in the opposite direction, then the current will flow in the opposite direction. So any two of those bullet points will give you the 2 marks. That brings us to the end of question number 4, and I will see you in question number